Dear students, I am very happy that to present today. We are dealing with unit number 3 at present in the class. So I have taken some questions from the university questions belongs to unit number 3, graph theory. Unit number 3 is graph theory. So this is one of the university question which appeared in 2020 November 2020. This question comes from Anna University. Now let us take third unit question, 2-mark question first, and this is what: define a complete graph. Define a complete graph. That is what the question is asked in 2020 by Anna University. Now let us discuss about that. Define a complete graph. Now I do want to open the screen, and this is what the definition of that. In a graph, if each pair of vertices is joined by an edge, then it is called a complete graph. So a complete graph is a graph in which each and every pair of vertices are connected by an edge, or there exists an edge between any two vertices in the graph. Then that graph is called complete graph. Now look at that. Now this is one vertex, this is another vertex, this is third vertex, fourth vertex, fifth vertex. I am calling it by V1, V2, V4, V5 and V6. Now I am joining each and every vertex. I am joining each and every vertex by edges. Now look at that. V1 and V2, I have drawn one edge. V1, V6, another edge. V1, V5, third edge. V1 and V4, fourth edge. That is, from the first vertex I have made edge to each and every vertex. That is, from V1 to V2, V1 to V4, V1 to V5 and V1 to V6. Now similarly, from V2 to V6, V2 to V5 and V2 to V4. Now what I see here, V2 is also connected to each and every vertexes here. V2 is connected to V1, V2 is connected to V5 and V2 is connected to V4. Now coming to V4, V4 I am connecting to V6, V4 I am connecting to V5. So there exists edge between V4, V2, V4, V1, V4, V6 and V4, V5. So this one vertex is connected to all the vertices. Now the last one is about V5 to V6. V5 to V6. So now this V5 is connected to V4, V5 is connected to V2, and V5 is connected to V1, V5 is connected to V6. Now come to the last vertex here. Now V6 is connected to V1, V6 is connected to V2, V6 is connected to V4 and V6 is connected to V5. So what I understand here in this graph, what I understand is that each and every vertices, every pair of vertices have an edge. These two pair have an edge, 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 so like that. So each and every pair have one edge, and such a graph we call it as complete graph. Okay, so what is your understanding? In a graph, if each and every pair of vertices are connected by an edge, then that graph is called complete graph. No one should not be without connection. No pair should not be without connection. All should have connection with other vertices. Again, such a graph we call it as complete graph. Yes, welcome students. In today's discussion, we are going to take this university question. This is from Anna University, and in the year 2024, just last year, in April, May, this question was taken by Anna University and distributed to the students for answering. Now I am interested in discrete mathematics, that too in unit number 4. The unit number 4 is a dish. Okay, unit number 4, the question is the set of integers under ordinary multiplication a group? Is the set of integers under ordinary multiplication is a group or not? Now let me prove this. Now understand that this is a group or not. That's what we have to understand. Now the question is the set of integers with ordinary multiplication a group? So we are going to justify that, whether it is true or false. That is what we are going to justify. Now the set of integers with ordinary multiplication is represented as like this. So any structure, algebraic structure like this, a set with some operation we call an algebraic structure. This is group or not? That is what our question is. This a group? That is what our question here. Okay, so now to prove a group, the structure is called a group. It has to satisfy 4 important conditions. First one is closure property, second one is associative property, third one is identity property, and last one is inverse property. Okay, so this is called a group. It has to satisfy closure property, associative property, identity property, and inverse property. Now here the set of integers, we know 0, 1, 2, 3, 4, 5, 6, minus 1, minus 2, minus 3, that is called the set of integers. This is multiplication operation. So that is closure. Okay, that is this set with this operation is closed. Similarly, this set with this operation is associative, and also this z, that is set of integers, have the identity. The identity this particular set have with respect to multiplication, that is 1. 1 is the identity for this group. Now the last one is inverse. Okay, so this inverse have some problem with this algebraic structure. Now let us look at that. Suppose A belongs to Z, then E also belongs to Z. Here as I already told you, this is the identity in Z. Okay, then uh, to say that A is having inverse, it has to satisfy one condition, that is A into, that is multiplication operation, that's what is given here, A into any number belongs to Z, you must have 1. This is a condition for inverse. That means for every A there exists a number. When you operate this operation here with that particular number, you have to get the identity. For all elements A, there must exist some element in A dash, so that if you multiply both of them, you must get the identity 1. But here the possible number is 1 by A. If you multiply ordinary multiplication of A by 1 by A, you will get 1. But this 1 by A does not belongs to Z. That's the problem here. But what's the problem here? 1 by A does not belongs to Z. So this number also must belongs to Z. For each A, there must be an inverse, such that if you multiply any number by its inverse, we have to get the identity number. But here it is impossible. 1 by A is not in Z, because in Z we have only the number 0, 1, 2, 3, 4, or minus 1, minus 2, minus 3, and fractional number will not come in the set of integers. Therefore we cannot find such a number in Z. Okay, so which implies inverse property or condition is not satisfied in Z comma X. Therefore Z comma X, the algebraic structure, is not a group. We cannot say that Z comma X a group. It may be algebraic group, but it is not a group, because the inverse condition is not satisfied. So thus we can answer the question here. So I repeat again, the set of integers with multiplication is a group or not. That's what they check. To say this algebraic structure a group, it has to satisfy 1, 2, 3, 4 conditions: closure, associative, identity, and inverse. These 3 conditions are satisfied by this operation on this set of integers. But one condition, inverse, is not satisfied, because what the inverse condition says that for all A belongs to Z, we must have an E belongs to 1 such that this, but already E is present in G. This is identity element, we know. For all A, we must have a number like this. When you multiply this and this number also must belongs to Z, such that the operation of any element by this number, we must have identity. But here 1 by A only suits this situation, but 1 by A does not belongs to Z, because Z consists of all numbers 0, 1, 2, 3, 4 like that, and minus 1, minus 2, 3 like that. So this fractional number will not come in Z. Therefore we cannot find for all A such that if you multiply that with this number, we are getting an identity. So inverse condition is failing here. It is not satisfied. Therefore this algebraic structure, that is this one, Z comma X, where Z implies a set of integers and this denote ordinary multiplication, is not a group. Thank you very much.